A couple of words before starting with the talk, a bit of introduction about ourselves. So my name is Marco Squarcina. I come from Venice, Italy, the actual Venice island. I got my PhD there, and then I moved to Vienna in Austria, where I'm working at the TU Vienna as a senior scientist. I'm a CTF player. I started many years ago in 2009. I'm the co-founder of Maccheroni, which is the best possible name for an Italian hacking team. Gonna play DEFCON CTF in a couple of days after presenting this work also at Usenix and coming back to Vegas. I sleep at the Venetian just like to feel more at home. I'm also involved with the IT security education activities in Europe. I collaborate with the European Union Agency for Cybersecurity and with other national initiatives.
Hi, hello everyone. My name is Pedro Adão. I'm born and raised in Lisbon. I love my hometown. I stick around. I'm an associate professor there at Técnico, the engineering school of the University of Lisbon. I started in programming languages and web security, and I'm originally a mathematician, and by accident, my path crossed with Marco in 2013, where I played my first CTF, and since then, I just became addicted to that. So basically, I went back home, I founded the team at our university, and then I also became engaged with many other activities, such as the Portuguese team for the European Cybersecurity Challenge, and I'm also the proud coach of the Team Europe that participated in the European Cybersecurity Challenge and won last week for the second time in a row.
All right, so in case it is not clear from the title of this talk is about cookies. We all like cookies, but cookies have a problem, which is well known. Cookies have weak integrity. And typical attacks that you can mount because of weak integrity involve session fixation and login cross-site request forgery vulnerabilities. Then over the years, there was a large body of work on this field, including advanced CSRF attacks, discrepancies that are exploitable between clients and servers, and application-specific vulnerabilities. All these problems, anyway, are deep-rooted into the standard itself. So again, known problems that are formally encoded in the standard. This is a section from the RFC 6265 bis describing the main issues that now Pedro will recap so that we're sure that all of us are on the same page.
Okay, so one known integrity problem with cookies is that cookies have an attribute that is the domain. And so if an attacker controls a subdomain, the attacker can toss cookies with the domain value of the original domain, in this case example.com, and these cookies will be attached to any request that is done to example.com and to any of the subdomains. There's also another attribute that is called the path, and the path can be used by the attacker to prioritize the cookies and the way that they are sent to the servers. An interesting attribute that is SameSite, it helps in the attacks that we are going to see, but in our particular context, we are attacking from SameSite, we are exploiting SameSite attackers, and so that will not be useful for us. Bear in mind that although the cookies have all these attributes are not sent to the server and so the server cannot really tell apart which cookies are set by which entities. Another known integrity issue is cookie eviction. So basically, implementations of cookie jars have a limit, and if the attacker sets too many cookies, it will eventually evict the oldest ones. So one attack that the attacker can do is that the attacker can just set, let's say, 200 cookies, evict the old ones from the cookie jar, and this can even happen for cookies that are HTTP only. So HTTP only provides confidentiality against cross-site scripting, but does not provide any integrity.
Yeah, so that we are on the same page again, talking about threat models. These attacks that we're going to showcase today are enabled by two possible threat models. The first one is the SameSite attacker, typically enabled when you control a subdomain using like subdomain takeover exploit. We did also more formal research in 2021, presented at Usenix, where we try to measure the import of these attacks. And indeed, we found more than 1,500 vulnerable subdomains across prominent sites like CNN, F-Secure, Cisco.com, Lenovo.com, and so on and so forth. We also studied those situations that promote automatically an attacker in a same-site position without doing actually anything. And these are all the problems that are due to the limitations of the public suffix list. We don't have time to dig into that today, but you can imagine corporate networks, dynamic DNS providers, and roaming services. For what concerns the network attacker, there is a good protection out there. It's the HSTS header that forces the browser to have connections only over HTTPS on a website, including all possible subdomains of that host. But unfortunately, deployment of this protection is still partial. 90% of the websites are still vulnerable because either missing HSTS header or missing include subdomain directive.
OK, so we'll start with cross-origin request forgery. So we call it cross-origin. So we control a subdomain, so it's not cross-site. For us, the attacker controls a subdomain. And so in this case, the same-site cookie attribute does not help us. So we have to rely on the existing tokenizer patterns for CSRF protection. And one that exists is the double submit pattern. So the double submit pattern basically consists in whenever to perform a protected action, the Bob has to submit a random token and the cookie that matches the token in order for the action to go through. The wrong assumption here, that's why it doesn't work in the case of same-site attacker, is that usually the attacker can only manipulate the token, but in this case, he can also manipulate the cookie. So it's trivial for the attacker to toss a coin, to toss a cookie with the value that the attacker will later use to perform the CSRF protected action, and so obviously it will be accepted. OK,
so this is a known problem. How do you protect against a same-site attacker against this CORF of vulnerabilities that you just introduced?
OK, so for same-site attackers, we have to use the synchronizer token pattern. And the idea behind the synchronizer token pattern is that each session, either stored on the server or on the client, it doesn't matter, this session is assigned a random secret. And tokens are random tokens derived from that secret. The validation is done upon receiving a token if the token that was received is compatible with the secret that is in the session. And if that happens, then it is accepted.
But can't the attacker still overwrite the session cookie containing the secret?
Yeah, good question. The attacker can still overwrite the session cookie, but by overwriting the session cookie, it also de-authenticates the user. So yeah, that's not very useful to perform a CORF attack. So we started studying this. Marco, in fact, stumbled upon this weird behavior while he was developing a CTF challenge. And basically, we started with Flask. Flask is a micro-development framework that does not provide any user management nor CSRF protection. For that, you have to include external libraries, in this case, Flask Login and Flask WTF. And Flask stores the session on the client. And the tokens are generated as an HMAC of the secret that is in the session plus the expiration time. You can see here that basically upon login, Bob gets a token T0. And then when Bob logs in, Bob sends the username, the password, and the token, and gets a new token T1 that can then be used to perform the protected action.
This is fine, right? Because if the attacker overwrites the session cookie, then there is no way to have the user still authenticated. So that's good.
Yeah, well, it is. But if you look carefully, you notice that the secret that you used post-login is exactly the same secret that is used pre-login, which means that the tokens that were generated up front before the login, they are still valid after the login. So what the attacker can do is that the attacker can just access the login form, get a token T0, then toss this session that the adversary obtained towards Bob's browser. And when Bob tries to log in, what we are doing here is the equivalent to an unauthenticated session fixation. So when Bob logs in, Bob gets a new session, this blue session, but the blue session still shares the same secret as the pre-login session, which means that the attacker has a token T0, that first one, that is still valid in the blue session. So the attacker can just send this token, T0, and perform the protected action. Okay? So basically, we found these CORF token fixation attacks that bypass the synchronizer token pattern. And the root cause is that the secret that is used to generate tokens after login is the exact same one that is used to generate the random tokens prior to the login. We tested many frameworks. Some store session client side, some store server side. The problem is exactly the same. So you may ask, but what happens if the user is already logged in? Well, if the user is already logged in, we just go back, use the eviction technique, de-authenticate the user, and then start the attack as we just saw. So while doing this, we started studying many frameworks, and one of the frameworks we studied was this code igniter. So basically on the right-hand side, you have what is the session object on the server, and what we highlighted is the secret. So before login, we have this session 0 and the token T0, and the secret is this 47 whatever. And basically when Bob logs in, he gets a new session S1, and you see that the secret now changed. So
I mean, this is perfect, right? Because the two secrets are different, so there is no way to get like a previously issued token and then use it like after authentication.
Yeah, it was, but it turns out that the session that existed prior to login, it was also updated. So although the secret is new, session 0, the one that the adversary has access to, that session is still, it's also updated with new secret. So the adversary can now generate again tokens that are valid for the new secret that are exactly the blue secret. So the way it goes is that we just do the pre-login and session fixation again. Bob authenticates. Now T0 is no longer valid because the secret is different. But what attacker can do is that the attacker can ask for a new login, get a fresh token that shares the same secret as the blue one, this T2 token, and now use the T2 token because session 0 and session 1 share the exact same secret, so they generate compatible tokens. So we did this for 13 frameworks that were the top according to some GitHub metrics, and some of them were using quite relevant modules with 2 million downloads per week. And we found among these 13 vulnerable web frameworks that 9 of them were vulnerable to some sort of attack. So 7 again had the synchronizer token pattern implementation broken. 4 of them used default double submit pattern, and 3 of them have the session fixation still. We can still perform session fixation attacks. So this was our study, and all of this is related with session integrity. So, Mark, are the cookies getting better now?
Yeah, this is a good question, and it's not really easy or straightforward to answer it, because it's not just about like checking the standard and saying like if there are new features being added there. It's also checking implementations on browsers and the server side. And that's how we approach the problem. So we started revising the standard, the RFC 6265 bis, and then we implemented a browser testing suite with all known cookie integrity attacks, so all cookie tossing and eviction techniques, and we tested them against the 3 main browsers, so Firefox, Safari, and Chrome. Whenever we found a discrepancy in the behavior, we went back to the standard and we tried to understand who was doing the right thing or the wrong one. And then we did something similar also for the servers. So we implemented a very simple differential fuzzer. We generated a lot of input for the servers, so basically like, differences in the cookie header. And then we started recording all possible discrepancies. Whenever we met a discrepancy, then we manually analyze it and try to understand whether it was possible to mount an attack using it. Talking about the standard, there are like 2 main changes that happened a few years ago. The first one is called the strict secure, and it's against the network attackers. The idea is that if you have in the cookie jar for your site a secure cookie named, let's say, test, and the network attacker tries to set from a non-secure origin a cookie named in the same way, so test, the browser will block it. It's not possible to set it to perform cookie tossing from a non-secure origin, all right? The second and most relevant protection in the cookie domain is the cookie prefixes. There are two prefixes. One is __ secure, the other one is host. We'll just focus on host in this talk. The idea is that if the cookie name starts with __ host minus, there are additional security restrictions put in place by the browser, all right? The first protection is that the cookie must be set with a secure attribute. The second one is that the path attribute must be set to /, so it's not possible to do like some magic tricks to prioritize the cookies set by the attacker. And the last and most important point here is that the domain attribute is disallowed. So you can't toss a cookie from a subdomain using this protection. That's why we call these cookies high integrity or domain or host locked, okay? I got a trivia for you. So on the left-hand side of the screen, you will see some set cookie headers. And you have to tell me if you think this is valid or if Chrome and Firefox will reject them. If you think that they're valid, try also to imagine what could it be the corresponding cookie header, all right? So let's try with the first one. Do you think that set cookie foo equal is valid? Raise your hand if you think it is. All right. It's a bit difficult for me to see, but yeah. Do you think is not valid? Raise your hand.
Valid one.
OK. All right. Second one is equal to foo. Third one. So set cookie equal foo equal. Is it valid? Raise your hand if you think it's valid. OK. Invalid. OK. Several hands.
It's a tie.
Third one is set cookie equal foo. And the last one is a bit weird. It's set cookie foo with no equal symbol. Is it valid? All right. Is it invalid? All right.
Valid wins.
OK. OK. So the first one, as you correctly guess, is valid. It corresponds to a cookie named foo, but with empty value. And it's also parsed by the server. In this case, we are taking into consideration Werkzeug, which is the middleware used by Flask-based Python applications. And it's parsed correctly. There are like no discrepancies whatsoever. The interesting thing here is that all these headers are valid. And they correspond to cookies without a name, or like where the name is an empty string and different values. The concerning bit is that the cookie number 1 and the cookie number 3, they are serialized exactly in the same way. So the corresponding cookie header using the request is foo equal, but it maps to different cookies. In the first case, to a cookie with the name foo and empty value, and in the third case, with a cookie without a name and with value foo equal. Now you might wonder, how will the server parse all these different cookies? Of course, exactly in the same way. All these cookies are the same for the server due to, well, like lack of support for the standard and additional vulnerabilities that we found. So basically, Werkzeug was stripping the leading equal symbol from the cookie header. OK, so this is an implementation mistake for Werkzeug. But what's the case for Chrome and Firefox? Why do they behave in the same way? Isn't this an implementation glitch? Unfortunately not. This is part of the standard. Nameless cookies are called, and they're being supported starting from 2020. And also this serialization collision that I just mentioned is also part of the standard.
OK, these are fun facts regarding cookies, but how can we leverage them to do something in security?
So I introduced 2 security protections before because I want to break them with this technique. So how to do that? So how to bypass host cookies? It's actually pretty simple. So imagine that you have bank.com setting a legitimate host cookie with a secure attribute and the pet attribute set to /. From a subdomain attack.bank.com, we can set a nameless cookie having as a value __ host minus ses equal to bad with a domain attribute, because for the browser point of view, this is a normal cookie with no additional security restrictions, all right? And so the browser due to the serialization collision that we introduced before, we just serialize the two cookies exactly in the same way, making it impossible for the server at bank.com to distinguish between the two. So we disclosed these issues with, well, first we started a public discussion because we didn't fully understand at first the security implications of this thing. And then we realized that it was indeed like possible to bypass those prefixes, and we opened two different issues with Chrome and Firefox. Let's give credit where credit is due. Axel Chong reported these two vulnerabilities just a few days before us, but then our issues got merged together. We discussed protection and additional edge cases. How was this thing fixed? A reasonable person would assume that you just nuke nameless cookies from the standard. Unfortunately, this is not what happened, and nameless cookies were just patched so that nameless cookies are still supported by browsers and by the standard, but if you try to set a nameless cookie having as a value something that starts like a non-case sensitive match __ host minus, then the browser will discard that cookie. All right? Is it enough to fix all the issues? Obviously not, because if you have an HTTP processing chain with an additional cookie parser in between, as it was the case of Amazon API Gateway, then you still have the vulnerability even if you're using a fixed browser. So we reported that, and the gateway implemented the additional protection that is now also landed in Firefox and Chrome. Safari was not affected because it diverges from the standard. Let's see now something that still works. So we have strict secure, and you can leverage this technique of nameless cookies to bypass a strict secure. The idea is like the same as before. So you have a session cookie. So the cookie is named session with value good. And from a subdomain, you set a domain cookie that is nameless and has as a value session equal to bad. Then serialization collision, and you can see that in the cookie jar you have one cookie that is secure, the other one that is not secure, but they are sent together to the server. First one usually takes precedence from like the server parser, and then you can bypass the protection. We also investigated other servers. There are more results in the paper. Please check it out. I will link it at the end of the presentation. And we found out that the legacy design of register globals, maybe some of you here remember what is register globals, affects also the cookie superglobal array. Meaning that if you send the cookie header where the name contains some characters like space, dot, and open square bracket, these characters are replaced with the underscore symbol. So all the cookies that you see on the slide, they are parsed exactly in the same way. And then from a subdomain, you can set underscore space host minus ses. For the browser, this is a normal cookie, no additional security restrictions. But for the server, this is equivalent to a proper host prefix cookie. We also investigated, as I said, browsers, and we found interesting issues with Firefox. So we tried here to mount an attack, well, to test the attack against strict secure cookies. So you have bank.com setting a cookie named ses with a secure flag on, and then from a non-secure origin, bank.com, we tried to set via JavaScript a cookie named in the same way, so ses. You would expect that the cookie is not set in the cookie jar, which is indeed true. That's exactly what happened. So far, so good. The problem was that if you try to access document.cookie again from the non-secure origin, you could still get ses equal to bad. So it's like some weird setting in which you have the cookie jar that is fine, but then the value returned from the JavaScript API that disagrees with the content of the cookie jar. We call these issues desynchronization issues, and the interesting bit in this case is that it wasn't just a mere implementation mistake, but it was due to a too strict isolation because of the implementation of site isolation that is called project fission in Firefox. So you have basically two different processes, one rendering the HTTP origin, the other one rendering the HTTPS origin, and they do not talk to each other, so they do not understand that they can't know who set what. Another desynchronization issue that we discovered was when performing a cookie jar overflow. We could set via JavaScript more than 180 cookie. That is the typical limit of Firefox for the cookie jar. And again, like these are not cookies that are flowing into the cookie jar. They just remain in the document.cookie API. The funny thing is that these cookies are not deletable. They are kind of immortal. You can try to use like a clear site data header. You can try to set them with an expiration date in the past using set cookie, or even manually. You open the developer tools and you try like to remove them manually. The document.cookie API still returns them. Okay. What's like the problem with this? There are some front-end libraries that are relying on the value of document.cookie to then create custom HTTP headers, as in the case of ASP.NET and Angular, to implement CSRF protection for custom fetch requests. And that's it. That's the way the cookie crumbles. Thanks very much for your attention. A couple of takeaways from this talk. The first one was that we were really shocked after analyzing libraries that are very well battle-tested. That was the case of Passport, for example. We're talking about 2 million downloads a week, still vulnerable to session fixation and to other things. The question here is that, like, the first one is, what's the status of applications, of websites in the wild? Because if you have these problems on frameworks that are the backbone of applications out there, I'm wondering, like, what's the situation for, like, a normal website? And then, like, what's the root cause of these issues? Is it a problem of a composition of different libraries that they do not know what the other library is doing? Or is it a lack of understanding of the threat model? Second takeaway is the legacy design is still cursing our applications, not just at the implementation level, which will be, let's say, more understandable, but also at the specification level. That was the case of nameless cookies. And this is really worrying. And we should try to find a way to move out of legacy design and have a better, more secure by default web. Last point, if I had to pick a point, it would be like the last one, is that web security is still evolving in a very disorganized way. We saw that you can't just like fix one side and then have like security for free everywhere. Web security should be a joint effort, and web developers and developers of the web frameworks should be in the position of being up to the latest developments of the specs and the latest behavior of modern browsers. Please check the paper and the artifacts. There is more stuff there. There is also a measurement of nameless cookies and host cookies supported in the wild. And that's it. If you have any questions, we're happy to take them, but we will also be in the room in front of us to take your questions later and have like a more informal chat if you want to. Thank you.
Thank you.